And then Vinny, Nick, and Ethan get ready to go. About 1 minute, and we'll have you guys start. All right, gentlemen, whenever you're ready, go ahead.
All right. Hi, I'm Vincent Finucci.
Hi, I'm Nick Reimers.
I'm Ethan Santana, and this is the Ice Tornado.
You hate when your car is way too hot when you try and get in after a long day of work? Do you ever feel like the man in the picture on the left when you get into your car? We designed the Ice Tornado to make you feel more comfortable in your car after a long day. When left in the sun on a concrete or asphalt flooring, cars often get very hot. As seen in Figure 1, the temperature of the air in the interior of the car rises very quickly. The National Oceanic and Atmospheric Administration shows that the average temperature across the United States during July 2020 was 75.7 degrees Fahrenheit. Based on Figure 1, after an hour at 75.7 degrees, the air temperature in the car would be approximately 118 degrees Fahrenheit, a 43-degree increase. Figure 2 shows the different temperatures of each component of the car, such as the dashboard, steering wheel, and seats. It also shows the difference of being parked in the shade versus the sun. As you can see, the air temperature inside of the car still gets very hot even when you park in the shade. It is upwards of 100 degrees Fahrenheit. Our goal is to cool the air inside of the car down to a safer temperature below 90 degrees Fahrenheit.
These are some of the solutions we could find. The AutoVent is a solar-powered fan that you can hang from the window, meaning that you have to leave the window cracked, which could lead to someone breaking into your car. And also the fans were not powerful enough to actually cool the car down. Similar to this product is the USB powered car ventilator. This device also has the same problem. The car cannot get cooled down enough, even with the 3 fans. And you also have to leave the window cracked as well. The Sunshade is a pretty good product to keep the sun out of the car, but the problem is it only blocks the sun from the front of the car, not the side or the back, meaning that the sides of your car can still heat up. The Lombo is a great product that works really well, easy to set up, and it keeps the car cool, but it's around $400, so it's not very affordable, and it's also not very convenient to take to work. We came up with several designs. These are just a few of our best. The 3 on the left are the tube fan idea, then there is a cooler idea, and then there's a insulated blanket idea. And then in the middle, we have a solar powered box that has an ice in the bottom that blows cool air out of the box. Then there is a fan that is basically just a normal fan that clips to the sunshade that is then blows the cool air from underneath the sunshade to the rest of the car. We decided that the tube fan design was the best idea. The design has 2 tubes, one that is bigger and then is made out of 4-inch PVC pipe, and then one that is smaller and is made out of 1.5-inch PVC pipe, or steel pipe, sorry. The design has 2 fans, one that blows air into the tube and one that blows air out of the tube. There is a gap between the tubes in order to keep the gel packs inside. The packs cool the smaller steel tube, which will cool the car once the air is blown out of the tube. And then the PVC pipe holds the gel packs in place and acts as insulation for the design.
Here are some principles that were applied to our project. To begin, we did research on the heat capacity of different materials that we were planning on using to put inside the PVC pipe. We end up choosing an aluminum pipe because of its low heat capacity, along with it being within our budget. The second thing that we did was also research the heat capacity of liquids that we're trying to use to put in between the two tubes. However, we also wanted to make sure we picked the best material here that would last the longest. So we did an experiment where we grabbed 4 different solutions, one being just plain water, 2 being antifreeze solutions, with one being 50% antifreeze, 50% water, and another one being 70% antifreeze, 30% water. And the last solution was this plastic marble gel that is used in Blue Apron cool packs. We threw all 4 solutions in the freezer, froze them overnight, and took them out and measured them over a 2-hour stretch to see which one will last the longest. As you can see in the data, the plastic marble gel lasts the longest, and we decided to use that for our ice. Here we have the construction of the prototype. There are many steps that were taken in order to get this done. One of the most important ones was 3D printing a cap that can go on each side of the tube that can hold the fans in place and also hold the aluminum tube inside. This was difficult and hard to do. Luckily, Nick Ramos was able to get this done for us. We also had to get the gel packs into little plastic baggies in order to enable them to fit in the two pipes. We also had to froze them in an angle so they would fit. We also had to cut our PVC pipe the same length as the aluminum pipe. And the last thing that we did was setting up and coding an Arduino to run the fans when the temperature sensor reads 32 degrees Celsius or 89.6 degrees Fahrenheit. Our design specifications and the test results for each design spec. For our first design specification, we wanted to cool the car off to 90 degrees Fahrenheit. For this test, we just threw our device in a car and had a LabQuest record the temperature throughout an hour test. As you can see from our data, it did keep the car underneath 90 at several different time intervals. This is because we programmed our Arduino to run the fans when it is above 89.6 degrees Fahrenheit. And it will run it for 10 minutes straight. After 10 minutes, it will once again read the temperature sensor to see if it is above that mark. If it is, then it keeps the fans going. If not, then it turns off the fans. We did this to save battery power, so the fans weren't constantly running. And it obviously, as you can see in the data, it did work. We started with a 97.3 degrees in the car, and it dropped all the way to 91.6 after 10 minutes. And then since the temperature was still above 90, we kept it going for another 10 minutes. And after 10 minutes, it was at 85.9, so the fans automatically stopped. Sorry? Anyway, 85 point, at the time mark 20 minutes, it was at 85.9 degrees, so the fans turned off, and the car began to heat up again. As you can see in the graph, there's a slow decrease in time, and a slow decrease in temperature throughout the first 20 minutes, and then a sudden rise because the car was able to heat up. However, since we did keep the car underneath 90 degrees Fahrenheit, we do believe we met this design spec.
All right, for the second design specification, we wanted a standalone power supply. For this, we wanted it to be independent from the car because it would drain the car battery if it was not. So we were going to do solar power, but we decided on 2 rechargeable 9-volt batteries because our design lasted 6.5 hours with the fans constantly running with those 2 batteries. Although our fan is not meant to last 6.5 hours with it constantly running, because the fans will only turn on when the temperature is less than 90 degrees or more than 90 degrees. With this design spec, with the 2 rechargeable batteries, we met this design spec. The third design spec is usable on all kinds of vehicles with roofs. The reason that this design wouldn't work with cars without roofs is because the cool air would escape and therefore not cooling the car off. So the design is small enough to fit in all vehicles that will, with all vehicles, that design that can be placed almost anywhere in the car, on the floor, in the seat, or in the center console. The fourth design specification is it won't permanently or modify the vehicle. The reason behind this design specification is because it would be a lower price in order to sell it in the future if you modify or damage a car. And then we took into account condensation could damage the car, so we added a towel to prevent that. Since our design can be placed almost anywhere in the vehicle without having to modify or damage it, we met this design requirement.
Our fifth design specification was to make the device portable. We specified this as a device that has a maximum of 30 pounds and can be carried from car to car. We had our tester carry the device to his car, and he was easily able to carry both components, one in each hand, to his car. As seen in the first two images, the combined weight of both parts is about 4 pounds. We added in the weight in grams and then converted it to pounds, as it is difficult to see the scale. Some of the designs in a prior solution, such as the auto vent, were much smaller and could fit into your pocket, but it was much less effective. The Ice Tornado meets this design specification as its weight is under 30 pounds and it can easily be transferred from car to car. Our sixth design specification was to have the setup quick for day-to-day use. We set a time constraint as a maximum of 30 seconds to fully set up the device. As shown in the diagram, the 4 test subjects set up the device in under 30 seconds. Coach Guy Sabala is seen in the video, and he fully set up the device in 27 seconds. These tests were done with simple instructions on how to set up the device, as there would be an instruction manual in any final model. The tests we have done on the device have all been under simple instructions and have all been less than 30 seconds, so we have met the criteria for this design specification.
For our seventh design specification, we want to test the usability. We want there to be usability within our device. And to keep the device within 4 buttons start. However, there are no buttons to start the device, but now steps one will have to do in order to set up and start the device. We were unsure as how to test this part of our design, so we consulted our engineers, and they told us to give our device to someone and have them figure it out without telling what to do. This is very similar to our test in our 6th design spec, but in those we showed the person how to set up the device. Here we just gave it to someone and just had them figure it out. We gave it to 4 people, and all of them were able to figure it out with only doing it 10 seconds longer than the one in the 6th design spec test. So therefore, we believe this was met. Here we have our final design. As you can see, the tube is wrapped in a towel to absorb any condensation, and the Arduino is in a box along with the little flap down for the temperature sensor to be out. Here, I'll play the video. This is our device working. As you can see, the temperature sensor is out and is currently reading over 32 degrees Celsius. Both fans are currently on. And see one side. As we go to the other side, you will also notice the fans are pointing in the same direction. That way, the airflow in the aluminum tube are going the same direction.
After all of the testing and the results we found, there are a few changes we would make in the future. First off, we would like to add a fitted towel that you could slide onto the Ice Tornado every morning. A fitted towel will absorb any condensation that would develop on the outside of the device. We would also like to improve upon the batteries reused. For the batteries, we would want batteries that will last longer than 6.5 hours. We'd want them to last ideally 8 hours for a full workday. But while for the test, the device ran continuously, so that's why they only lasted 6.5 hours. It would be ideal to have a battery that could last the full 8-hour workday running continuously. We would also want to direct more power to the fans, which we could have by using a different set of fans or by having more powerful batteries. Lastly, we would like to add in a stand that you could set the device on, and it will stay steady in the position you choose to put it in. We would like to thank everyone who helped us bring this project to fruition, especially Mr. Steckman, who was our mentor throughout this project, and the Carlsbad Educational Foundation.
Okay, I have a couple of questions. If you're ready.
Yes, we're ready.
Okay.
Okay. So I'm a little bit confused by the use model. So I take it that you put this device in the freezer and let it get cold overnight, and then put it in the car during the day, and that's where the cooling comes from.
Yeah.
Is that correct? Okay.
Yes, sir.
Okay. So you said that the batteries will last for 6.5 hours, but how long does the device itself stay cool? I have a hard time believing that you're going to be able to. You should be able to run the fans that long, but I have a hard time believing that the actual device is going to stay that cool that long. Is that did you test it for a long period of time?
I tested the gel for over 2 hour stretch, and it did not change a single degree. But then after, I just left it out even longer, and after about 6 hours, I saw it was still at 11 degrees Celsius, which was still pretty cold, which we believe will keep the circulation with cold air.
And that's continually running the fans that's in the car for that period of time, that 6 hours.
That 6 hours was just leaving out just in the same temperature. So, as I said in the earlier, in our in our STEM principles, I had 4 solutions all in the same degree and tested it over 2 hour stretch. But I was surprised with how well the gel did.
Yeah.
So I left it out for a little bit longer and tested it after 6 hours, and it was still very cold.
Okay. Well, I guess my suggestion would be to actually test it over that period of time that it would actually be used to show that, because that's really where the energy exchange is coming from, is transferring the heat from the car to that gel, or taking the heat out of the car and putting it into the gel. But since you're so far under your design requirements for size, you could always size it up if you really needed to. And the one suggestion that I might have, although, is if I'm at work, I don't really care about having my car being cool the entire time while I'm at work. I only care if it comes out, if it's cool when it comes out. So one thing that you could do to conserve energy and conserve some of your cooling is set a timer. So I could go into work and I could set it to come on maybe 20 minutes before I come out of work normally. So potentially you could save some energy that way. But very interesting approach. I don't think I've seen anything similar to that. It's a very creative approach to this problem. Nice job.
Thank you.
Thank you.
Fernando, you're muted, Fernando. Fernando, you're muted. You're still muted.
Okay, let's try this one. A little pop-up window came up and I hit unmute, and I guess that didn't work. I was just saying how it's pretty amazing how ideas come about, or problems. I wonder how you guys came up with this. Were you guys in like Death Valley and during the summer and said, hey, let's come up with this ice tornado? I love the product name. I love it. It's very catchy. How'd you guys come up with this idea?
The fact that Vinny has a black car, so his car always gets hot.
Yeah, so I play in golf tournaments, and oftentimes I'll play in El Cajon or Temecula during the summer, and I have a black car with a black interior, so it gets very hot, and then just having it sit outside for 5-6 hours a day in the weather, and then getting in after my golf tournament, I'll either like just the heat is kind of overwhelming when you get in, so I have to stay outside and let the car cool down for a while. And I just thought it would be nice to have something that could keep it cool and have it cool when I got in it.
I think I really enjoy these sessions with Mr. Fever. One, because I think everything you guys have learned in the last 3 to 4 years is coming together. Whether it's the design principles or how you go from during the product life cycle, let's just say, where you're brainstorming, or you're coming up with the concept. You're going through a development and prototyping and launching. So hey, I want to let you know that this is really what happens in the real world. I think what Mr. Fever has allowed for you guys to go through this process, this is a product life cycle. But in terms of as you think about this and as you productize a product, it needs to be making sure that it's manufacturability and that it's that it's well produced and consistently to your specs. What would you consider in doing if you want to productize this and have a systematic way where it's could be manufactured on a consistent basis as you improve your product? Any thoughts?
That's a interesting question.
Tough question.
Yeah. So as you said, in our future improvements, we would, want to have a sleeve on it. That way, the condensation doesn't get over the car, and have longer battery life along with better fans. There's a lot more that we believe that could have been better to this in order to cool it down even more. But yeah, that's a tough question though. So
and how's yeah, in terms of, I think as we think about prototyping and getting your first product, you got to think about okay, let's mass produce this. I think even as you gave the product to somebody without any instructions, a little simple way is just putting a letter on one thing and doing an A so they could match the A to the A, or color code red to red or green to green. It's little things like that visually. But as well, I think even as you think about the number of fans, the size of fans, does it impact your bottom line, your cost and your return on investment? Those are things as you not only just think of what you would do, but could consider those as well. Great job, guys.
thank you.
Thank you.
Yeah, great feedback. Thank you. Excellent job, gentlemen. Excellent job. So now we've got Nick, Madeline, and Gabe. So Nick, Madeline, Gabe, get set up here. You are all next up.